Hello again. This is the third speedrun of today, and we will be covering a lot more about transformations and about dilations in functions. So let's jump right in because we have a lot to cover. So the first thing you need to know is about reflecting functions in the x or y axes. And this is, I don't mean, yeah. So given that we have the function y is equal to f of x, well, if we have the function f of negative x, this will be the reflection of the original function in the y-axis. So it's like we have this function here, and we take the negative of it, well, it will look like this, the new function. Well, if we take the negative of the function, however, then it would be equivalent to a reflection in the x-axis. So let's illustrate this with like an x cubed graph. So we have the original function here in red. For f of negative x, which would be a reflection in the y-axis, this would look something like this. Oh, I realize this may not be the best example. Let's do a different function. Something that will look different. Let's say we have a function like this. Well, if we take the f of the negative x in the function, we reflect it in the y-axis. So we obtain a new function that looks like this. And if we take the negative output of the function, we reflect it in the x-axis. So the new function would look like that. Yeah. So that is the first thing we need to cover. Now, the next thing we need to cover is going back to our old friend, the vertex form. For functions like, well, we can express y is equal to x minus h squared plus k. We can represent movements in the function by changing the parameters of h and k, and the other way around, we can deduce from the new values of h and k what a new function is. So if we were to move, say, a function horizontally, if we were to translate it horizontally, this would be equivalent to adding to the h value. So the h, we add to the h some amount, yeah. And if we want to move it vertically, up and down, we would change the k value. So if h is greater than 0, then the graph is translated to the right. And if h is less than 0, then the graph is translated to the left. And the same if k is greater than 0, the graph is translated up. And if k is lower than 0, the graph is translated down. And so we often express these horizontal and vertical translations with a column vector called hk. This is like representing a shift of h units right and k units up. Of course, negative values being left and down. Okay. Now we need to talk about dilation. And this is the stretching of functions, either horizontally or vertically. So if we have a function y is equal to f of x, if we get a of f of x, this will be stretching the function vertically. So we have an original function here. Well, the new function depends on what a is. So if a is greater than 1, then the graph is stretched vertically. So the new graph would look like this, as long as a is greater than 1. But if instead a is less than 1, then the graph wouldn't be stretched, it would be compressed. And so it would be flatter than the original function. Looks something like that. Yeah. That's it for vertical dilation, and now we need to talk about horizontal dilation a bit, which is the stretching along the x-axis. So if we have our original function again, how we stretch it horizontally is we get f of a times x instead of a times f of x. So, of course, a being greater than 0, if a is greater than 1, then the graph is compressed. So for example, if we have f of 2x, then let me write that in a color. If we have f of 2x instead, then the graph will look something like this. Notice how it's not being stretched vertically. We still have the same minimum point. And if instead we have, say, f is equal to 0.5x, instead of compressing the function, we would be stretching it. And so even though we would have the same minimum point, values of x would be y. Yeah. So if a is between 0 and 1, then the graph would be stretched. If a is greater than the 1, then the graph would be compressed. And so yeah, more or less we can express all function transformations in the form of, well, from y, to translate a function from y equals f of x, we can express the new function in terms of y equals a times f of x, f of b times x plus c plus d. Something in this kind of form will allow us to obtain a new function. And it sounds very complicated, so let's move on to some questions to really see what we're talking about here. So I'm feeling like the odd question. Actually, yeah, I'm feeling like the odd questions today. So we'll be doing the first question, and we have the graph of f of x, where -3 is less than or equal to x, which is less than or equal to 6, and transform the graph according to, and we have some functions. So what does this initial function look like? It's not mentioned in the question because it's shown on the graph, so let me show you what the function looks like. It looks something like this. And now, the first thing we need to do is we need to graph g of x is equal to f of -x. So remember, if we take f of -x, it means we're reflecting it in the y-axis. So this new function would look like that here and there. So this would be g of x. So that's that done. Next we have h of x is equal to f of x plus 6. So what does this mean? We know that when we have f of x plus h, or actually it should be x minus h technically, we're shifting it h units right. Since it's x plus 6, it means h is equal to -6, and so we're actually shifting this graph, the original red graph, 6 units left. And so our new graph would look like something like this. So as you can see, we're shifting this original red graph left. I think technically we wouldn't draw the function after a certain point because it's not defined after that point. It's only defined while it is less than or equal to 6, but yeah. So, what is our next function? And our next function, our final one would be the graph of j of x is equal to f of 2x. So what would this j of x look like? I've run out of colors. I mean, I guess I could use like yellow. Okay. So remember f of 2x, if the number is inside the brackets, this represents a stretch or compression along the horizontal axes. And we will, f of 2x, yeah, no. It's a stretch or compression along the horizontal axes, and so we would stretch this accordingly. since we have 2x, this would actually be a compression since this number is greater than 1. And so our new function would look something like this. Yeah. And so this would be j of x. Yeah. Okay, so that was it for question 1. Now let's look at question 2b. Why not? So question 2 is write the functions r and s in terms of f. Sorry, we're shown functions f, s, and r, and we need to write r and s in terms of f. Okay, so we have the functions here, and we have r is equal to this, f is equal to that, and s is equal to this. Is equal to this. So we have this point over here as, let me label these axes. This is 4. This is 8. This is negative 4. This is 8. This is 2. Sorry, these axis scales are wrong, but we can still tell from these. And this is the origin, of course. So f of x, well, we know that f of x is the red line. So let's tackle r first. As we can see, r is a reflection of f in the y-axis. And well, what does that tell us? That means that r is equal to f of negative x. If you remember, this gives us the reflection in the y-axis. What do we have? Okay, next we have s. We need to write s in terms of f. So what's happening here with s is we actually have two different transformations. We have horizontal stretch, because as you can see, it goes from 0 to 8 instead of 0 to 2. And we also have a transformation downwards. And how do we express this? Well, we will express it in the form horizontal stretch is inside the brackets, so this would be f of, and it's stressed by a scale factor of 4, so this would be f of 1/4 x. Remember, this is opposite, and then we need to translate it downwards by 4, so we would go -4. So yeah, that would be it. Okay, so on to the next question. I will jump to 4, I think. Yeah, I'll jump to 4. And so question 4 will be to describe each transformation in terms of x. So our first question would be, these are the axes. We have f of x, we have g of x, and we need to describe this transformation. This is f of x, and this is g of x. And this transformation is quite simple. It's simply that g of x is equal to negative f of x, because as you can see, it's being mirrored in the x-axis, and when it's being mirrored in the x-axis, we know that we have to get the negative value of the original function. Next, we're going to function c. Oh, and that's the last one. Okay, so we have function c over here. And our original f of x looks like this. Oh. Up and up. And our new function looks like this. And sorry, if you can't see it from the bad scaling, there is no horizontal or vertical dilation in the function, and it's simply a transformation. How do we measure that transformation? Well, I guess we can get this point over here and compare it to this point over here. This point over here is 2, 0, and this point over here, sorry, I just didn't draw the axes, but this should be -1, -1. And so we need to transform the point 2, 0 to the point -1, -1, and that will be the column vector of -3, -1. So to get g of x, we have g of x is equal to f of x plus 3, because remember this should be minus h, and h is equal to -3, so minus 3 is plus 3, and we need to subtract 1. And yeah, that's it. So that was all for the speedrun. I now hope you're more confident in function transformations, and I hope to see you in the next speedrun. See you then!